In 1977, humanity launched two robotic scouts toward the unknown edge of the solar system. Voyager 1 and Voyager 2 carried cameras, instruments, and questions. Their destination was everywhere. Their true goal was the boundary between sun and galaxy. The paradox is striking. Our most distant explorers are not sleek modern hardware, but 1970s machines with laughably small memory. Yet those aging circuits are still sampling alien space. At the frontier of the heliosphere, old technology is rewriting new physics. Every atom in your body is ancient stardust, shaped by the same forces Voyager measures today. The magnetic fields, charged particles, and cosmic rays it detects also sweep across Earth. The probes sample the same galactic environment that quietly surrounds us now. The Voyagers existed because the outer planets briefly lined up in a rare configuration. Once every 176 years, Jupiter, Saturn, Uranus, and Neptune arrange so one spacecraft can slingshot past all four. Miss that window, and the grand tour becomes impossible for generations. To survive that decades-long trek, engineers chose nuclear batteries instead of solar panels. Each radioisotope thermoelectric generator converts heat from decaying plutonium-238 into roughly 157 watts. Not much power, but incredibly steady. Enough to run instruments, heaters, and a whisper-quiet transmitter far beyond Neptune. Redundancy kept them alive. 16 hydrazine thrusters, backup sets of critical computers, fault detection routines, and a high-gain antenna locked on Earth. Their transmitter is as powerful as a refrigerator light bulb, yet the deep space network still hears them as faint, regular radio pulses. Both probes threaded the asteroid belt, once feared dense enough to shred spacecraft. Instead, Voyager cameras revealed mostly empty space, scattered rocks, and distant boulders. They emerged untouched, heading into colder, darker regions where heaters mattered as much as cameras and spectrometers. 13 days after launch, Voyager 1 turned back toward home. From 11.6 million kilometers away, it captured Earth and Moon together, two tiny spheres of light. That early portrait foreshadowed a much more distant farewell image still to come. For nearly 2 years, the probes coasted outward toward Jupiter. Voyager 1, on a faster trajectory, overtook Voyager 2 and reached the giant first. Its cameras snapped images every Jupiter day, building a time-lapse of a world rotating beneath moving, ever-changing cloud bands. Then Jupiter filled the frame. Gone were blurry telescope views. Voyager revealed intricate belts, swirling storms, and the great red spot as a towering, rotating system. Two bright moons, Io and Europa, hovered nearby. Each would challenge our understanding of what moons can be. Voyager data showed Jupiter's atmosphere was far more violent than expected. Winds ripped east and west in alternating bands, but turbulence and plumes twisted everything into complex vortices. Smaller white storms spun beneath the great red spot, revealing an atmosphere crowded with long-lived tempests. Io changed planetary science overnight. Instead of cratered highlands like our moon, Voyager saw sulfur plains, dark calderas, and active volcanic plumes reaching hundreds of kilometers high. Tidal forces from Jupiter and neighboring moons continually flex Io's interior, keeping it the solar system's most active body. Europa looked completely different. Its bright, icy shell was smooth, etched by long, dark fractures and chaotic blocks. Craters were rare, suggesting a young surface. Voyager images hinted that beneath the ice lay a global ocean of liquid water, warmed by hidden tidal heating. Voyager also confirmed Jupiter wears rings. In backlit images taken as the spacecraft departed, a thin, dusty band appeared, glowing in scattered sunlight. Those delicate rings, completely invisible from Earth at the time, showed that ring systems are not Saturn's exclusive domain. Next came Saturn. From a distance, it was already spectacular, but Voyager 1's close flyby transformed the rings from a few broad bands into hundreds of narrow ringlets. Gravity and countless icy fragments combined into a shimmering, structured disk encircling the gas giant. Among those rings were mysterious spokes, broad radial shadows that seemed to drift across the B ring. They did not follow simple orbital mechanics. Leading ideas now involve electrostatic forces lifting fine dust above the ring plane, but Voyager's surprising images left important questions unanswered. Saturn's largest moon, Titan, hid its surface beneath a thick orange haze. Voyager instruments measured a nitrogen-rich atmosphere, denser than Earth's, with methane and complex organics. It was the first world beyond our planet known to have such a substantial, layered atmospheric blanket. Tiny Enceladus also hinted at something remarkable. Voyager saw a bright, icy moon with contrasting old and young terrains. Subtle evidence suggested material escaping into space, feeding one of Saturn's rings. Later missions confirmed towering water vapor plumes, but Voyager provided the earliest clues. After skimming past Titan, Voyager 1's path bent steeply above the ecliptic. It would see no more planets. Instead, it aimed directly toward interstellar space. Voyager 2, still within the orbital plane, stole that momentum for onward flights to Uranus and Neptune. Voyager 2 reached Uranus in 1986. The planet appeared almost featureless, a pale cyan globe with minimal visible cloud structure, yet its rotation was extreme. Uranus spins on its side, its axis tilted about 98 degrees, giving it seasons unlike any other planet. Magnetometer readings brought an even stranger discovery. Uranus possesses a strong magnetic field, but tilted about 59 degrees from its rotation axis and offset from the planet's center. As Uranus spins, its magnetosphere wobbles through space, defying simple models of planetary dynamos. Voyager 2 imaged Uranus's narrow, dark rings and discovered additional ones plus tiny shepherd moons keeping particles corralled. It also increased the known moon count dramatically, revealing a crowded system of icy bodies whose varied surfaces record impacts, tectonics, and buried internal heat. Among those moons, Ariel and Miranda stood out. Ariel's bright surface showed fault valleys and resurfaced plains. Miranda looked almost shattered and rebuilt, with towering canyon walls and strange racetrack-shaped regions. Voyager's images hinted at episodes of internal melting and resurfacing on surprisingly small worlds. In 1989, Neptune finally came into view. Voyager 2 revealed a deep blue world with high-altitude clouds racing around the planet. Measurements showed equatorial winds close to 100 kilometers per hour, making Neptune's atmosphere one of the most energetic in the solar system. Voyager found a huge storm, the Great Dark Spot, swirling counterclockwise with winds near 2,400 kilometers per hour. It also imaged faint, incomplete rings and visited Triton, where geysers vented nitrogen-rich material from a frigid surface capped by pale, pinkish ices. With Neptune behind it, Voyager 2 had completed the only grand tour humanity has ever flown. Neptune's gravity bent its trajectory below the ecliptic. Both spacecraft now sailed away from the planets, sampling a region dominated not by worlds, but by the sun itself. Before shutting down Voyager 1's cameras, the team granted a final request. From 6 billion kilometers away, the spacecraft turned its lens inward. One frame showed Earth as a pale speck caught in a shaft of sunlight, a now iconic pale blue dot. That single pixel is where every human story unfolded. The same fragile world whose magnetic field and atmosphere shield us from the cosmic environment Voyager now measures. Its perspective makes the emptiness between stars and the thinness of our habitable shell unmistakably clear. Beyond the planets lies the heliosphere, a vast bubble carved by the sun's solar wind. Inside, charged particles stream outward supersonically. Farther out, they slow at the termination shock, forming a hot, dense heliosheath, before finally meeting the interstellar medium at the heliopause. Models once pictured that boundary as smooth. Voyager measurements said otherwise. As the heliospheric current sheet ripples outward, then compresses, it fragments into magnetic bubbles. The outer heliosheath is a frothy, changing region of tangled fields rather than a neat, layered shell. On 25 July 2012, Voyager 1 reached that frontier about 120 astronomical units from the Sun. Plasma density around the spacecraft jumped roughly 80-fold. Galactic cosmic rays surged, yet the magnetic field's direction barely changed, contradicting expectations of entering a completely new magnetic domain. Voyager 2 crossed the heliopause in November 2018, also near 120 astronomical units. This happened during a more active solar cycle, when theories predicted an expanded heliosphere. Instead, the boundary lay at almost the same distance, revealing our earlier models of heliospheric breathing were incomplete. These crossings show our star moving through a magnetically disturbed region of our galaxy. The heliosphere shields Earth from much of the ambient cosmic radiation Voyager now directly samples. The same charged particles striking its detectors also occasionally collide with atoms in our atmosphere today. After nearly 5 decades, time is catching up with the hardware. Plutonium in the power generators slowly decays, reducing available electricity. Engineers shut down instruments and even heaters. Some components now operate far colder than their design limits, yet astonishingly continue returning usable interstellar data. In 2022, something strange appeared in Voyager 1's telemetry. Engineering data streams turned to nonsense, reporting impossible orientations and thruster states. Yet the science readings were fine, and the radio signal remained steady. The antenna still pointed home, even if the status reports disagreed. Investigators eventually deduced the attitude and articulation control system had started routing data through a long-retired faulty computer. The degraded unit corrupted outgoing engineering information. Commands instructed Voyager to switch back to a healthy channel, and after months of careful exchanges, normal telemetry returned. Glitches continued. Another computer problem on Voyager 1 in late 2023 again scrambled science data until engineers painstakingly restored functionality. Meanwhile, a mistaken command nudged Voyager 2's antenna just 2 degrees off Earth, severing contact until a powerful uplink pulse coaxed it to realign. Eventually, the generators will no longer supply enough power for any instrument or transmitter. The probes will fall silent, still coasting through the interstellar medium they briefly sampled. Their last detection of the heliospheric edge will stand as a benchmark for future explorers. Long after Earth's continents shift and languages change, the craft will keep traveling. In about 40,000 years, Voyager 1 passes near a star in Camelopardalis. Voyager 2 will approach Ross 248 and much later drift a few light years from Sirius. Bolted to each probe is a golden record, etched with images, sounds, and music from Earth. If some distant intelligence ever intercepts Voyager, that disk will offer a compressed portrait of oceans, animals, languages, and the physics students on Earth still study. Voyager revealed that our solar system ends not at Pluto, but at a dynamic, magnetically tangled frontier with the galaxy. Those measurements reshaped how we define our cosmic address. This is The Universe and Beyond, telling the continuing story of humanity's farthest explorers.